All right, in CAMI, we're going to look at the atomic theory models, and we are going to add a few drawings to this, and I'm going to remind you all that I am definitely not an artist, and I'm not going to grade you based on your artistic ability, but what I want you to be able to do is recognize certain things about these drawings. So you can get as close as you want to me, to what I'm drawing, excuse me. But anyways, we're going to start off up here in Democritus, and the first thing we're going to do is we're going to talk about the experiment that Democritus ran. The experiment he ran was actually just a thought experiment. He didn't do any data collection. He didn't go out and mix anything together. He didn't try anything. He just did a thought experiment. He sat around and he thought about this. And when he sat around thinking about it, when he sat around thinking about it, what he discovered, I've got to open up my window here. What he discovered when he was thinking about this is that he thought of the atom as just a big old sphere. So here we're going to draw a circle, and to make it into a sphere, to make it into a three-dimensional shape, I'm going to switch this one to blue too. We're going to draw that sphere like that. You can draw yours in whatever color floats your boat. Well, there's my sphere. It's a blue sphere. He didn't have any data, so it could have been blue, it could have been anything to him, right? And what we call this model, he thought of this thing as, not comment, I'm sorry, we're going to make a text box. He thought of this as atomos. Atomos, there we go, there's that spelling. And if you remember, atomos is Greek for indivisible, or indestructible, if you will. I'm going to move that to be right over there. So this is the atomos model, right? It's just a perfect sphere, is all it is. Then along comes, 2,000 years later, so next turn of the century, 2 millennia later, John Dalton sits down, and he's reading the same thing, and he does an experiment known as the multiple proportions experiment, where he eventually figures out the law of multiple proportions, right? That was the idea where he was taking carbon and oxygen, or nitrogen and oxygen, and if he found out if you mix them in different ratios, you get different compounds. And the only thing that made sense to him for that to be true is for there to be something that everything is made up of. And so here we're going to draw another. He didn't have any way to prove the shape of it, so his was a circle. Better than that, it was a three-dimensional circle, aka another sphere, right? So Dalton, being a British guy, thought about that sphere as a billiard ball, and nowadays we also think of them as a marble. Billiard ball, for those of you who aren't familiar with that, that's a pool ball, and they're well known for being nigh indestructible, and that's what he thought of the atom as well. So now we come down to Thomson, good old J.J. Thomson, another British scientist, and J.J. does an experiment known as the Cathode Ray Tube. So instead of just talking about that one, we're going to try and diagram it. We're going to try and draw the cathode ray tube. To do that, if you scroll down to the second page, here's all the experiments, and there's one labeled Cathode Ray Tube. So in that, we are going to draw, may as well stick with blue, and we're going to start with a rectangle. We're going to draw a big old rectangle, and underneath it, we're going to draw a triangle. Not sure where to start this triangle. Well, right there looks good enough. I'm going to move it so it's nice and centered. All right, there we go. Close enough. All right. Good enough for government work, as we like to say. So this glass, this rectangle looks like glass, right? Sure, it's a beautiful drawing of a glass tube. And so we're going to label that as our glass tube. And inside that glass tube, he placed metal like this, and then like this. There it is right there. Beautifully straight and perfect lines. Look at those gorgeous, beautiful, straight and perfect lines. And those two metal things, one was the cathode. Let's go with the text box. There we go. Cathode. Over at this end, and over at this end, we have the anode. And what he saw was that things would, he wasn't sure what they were, he just knew they were rays, and they would start at the cathode side and they move over to the anode. that wasn't good enough, right? He was actually not the person to invent this, right? That was William Crookes. But what J.J. Thomson did was he took and right over, somewhere right around here, he took and put a magnet. Beautiful, gorgeously drawn, amazing horseshoe magnet. Look how perfectly symmetric that is. Just fantastic. Anyways, that magnet, of course, sent out, some magnetism. We'll have magnetism coming out of that magnet. There we go. And what that magnetism did was, we're going to have the cathode rays now coming out of this thing. And those cathode rays, instead of going straight across, as they get close to that magnet, they would bend away from that magnet and then go down like this. And so we'll have another ray coming out, and it goes down like this. They're bending away from that magnet. Now, he could not calculate anything exactly about these rays. So we're going to label these guys as the rays. And then up here, we're going to put this as the magnet. We forgot to label the magnet. I mean, it was so perfectly drawn. Who would mistake that for anything but a magnet? But anyways, so because he knew the rays were made of electrons, he figured out, using physics and measuring the angle that those rays deflected, he was able to find the mass to charge ratio of the electron. Then he furthermore showed that the electron is negative. That was a very basic experiment, right? As soon as he put the magnet on there, the negative magnet, the rays would go away from it. The positive magnet, they would go up towards it. So that was, the first thing he kind of proved on this. But he was able to calculate that mass to charge ratio, and that becomes a super duper important thing a little bit later on. So let's go back up to Thomson. Thomson, again, hadn't shown anything about the shape of the atom, right? So we have to stick with a circle for the atom here. But what he did was, inside of there, he put tiny particles, like that one, like that one, like that one right there. And those particles, he knew, had to have a negative charge. Let's put that negative charge. Let's try and put it in the center here. There we go. Oops. Put another negative charge, center it. Put another negative charge, center it. Gorgeous, fantastic, gorgeous looking. Loving it. All right, so those negative particles he called electrons. And we'll draw, I know I'm loving my arrows lately. There's an arrow to the electron. So there's an electron. Actually, that's not a bad arrow right there. And that one could use a little work. Oh well. So there's these electrons. Now, he also knew from other people's work, if there were negative charged particles, there had to be positively charged particles. And by the way, one of those guys worked, Benjamin Franklin, right? So what he imagined was dispersed throughout this atom was a fluid, right? I don't know how you're supposed to have a fluid when, everything is, you're smaller than an atom. This was the idea he had. And the idea was that that fluid was positively charged. And that was all around these electrons. So this reminded him of Sunday evenings when he'd sit down to dinner, and his dear old mother would serve not blood pudding, but plum pudding. Plum pudding is a British dish. It has a lot of things floating around in it, and so that was what he imagined this was like a plum pudding. Like those electrons were just floating around in this kind of viscous, positively charged fluid. Interesting, huh? So Millikan comes along, and he decides he wants to find the exact charge, so he comes up with what's known as the oil drop experiment. We're going to go down here and we're going to draw the oil drop experiment and make a shape. It's a nice rectangle. We want to use a thick line on that because it was a, I would rather it be black than blue. Let's try that again. Let's make this one black. There we go. maybe a little less thick than that. Yeah, so nice thick drawing here. I'm going to move my picture over to this side. This is his chamber that he built. It would have been a steel chamber. It was actually a cylinder, but looked like a square from the side, so steel chamber. And in that steel chamber, I actually need to move mine over just a tad bit here. Well, if it'll let me. Oops. Oh, I see what's wrong. You got to select it. There we go. We got to move it over just a little bit. All right, so here's your steel chamber. And then what he did was in that steel chamber, he put what I'm going to draw next. Getting better and better using these drawing tools. They're a little rudimentary. What he put was going inside it. Out here we're going to draw like a little tube, and then attached to the bottom of that is a triangle, and on the top of that is a circle kind of poof ball, right? And so you squeeze this poof ball, and whatever's inside this thing gets sprayed out the tube. The technical term for that is an atomizer. An atomizer. And so he used an atomizer, and he filled the atomizer with oil. Filled that atomizer with oil. So whenever he squeezed the bulb, little droplets of oil, I'm going to make my oil kind of a greenish color. There it comes spraying out. Oops. Some of the droplets were bigger than others, right? Because an atomizer is not in a very exact way to make oil drops. So you'd spray those into the top part of this chamber. Well, the top part was divided from the bottom part by a plate. Again, we need kind of a thick plate here. And so there's the first part of this plate. This plate wasn't whole. It had a hole right in the middle of it. That plate, there we go. So there's a hole right in the middle of this plate. Furthermore, he attached an electrical wire to it, and he was able to put a positive charge on this plate. So there's a positive charge on this side, and there's a positive charge on this side. Where you got a positive, somewhere you got to have a negative, and so the negative part was that he put another plate down here at the bottom. So this plate right here, don't quite want it touching the sides, was a negatively charged plate. So negatives. And so what would happen is the oil droplets would come through there, and they would fall down, they would drop, literally, right? Oil drop, they would drop through, and as they dropped through, they would get repelled by this plate. And he could watch that happen because over here, over in the side, he built a microscope, but it's a microscope that looks a whole lot like a telescope. So he could look through this microscope and he could count those dots. And he could tell from the distance they were from that plate exactly the charge of the electron. So he finds the exact charge of the electron, and then he uses that to find the exact mass of the electron. He had Thomson's mass to charge ratio, and once you have the ratio and you have one of the numbers, you can easily find the other number. So that was the oil drop chamber. We're going to go back up here. What does that change about how we view the atom? Well, there is no change. Millikan's model was simply the plum pudding model. He didn't make any modifications to Thomson's model. The first person to modify it was actually Rutherford, good old Ernie Rutherford. He did the gold foil experiment. And the gold foil experiment, if we come down here, looks a little bit like this. We're going to make a shape here. We're going to fill it in. He built a giant lead box. Best color for lead is going to be black here. And that lead box had at the front end of it a whole bunch of stuff. But inside the box, what he did was he put a lump of uranium. So there's our lump of uranium. And so we're going to label this as, this thing is we would call it a radiation gun, because that is the most mad scientist thing ever. It's a radiation gun, and what it would do is it would let radiation out, come out the front end. And he had a sort of a trigger on this that would open it up and let only a certain amount of radiation come through. And specifically, the radiation that he let come through was alpha radiation. And he knew alpha radiation was positive. As we talked about yesterday, he saw how it bent in a magnet. And so this alpha radiation, there we go, misspelled radiation. This alpha radiation he knew was positive. So what he wanted to do was he wanted to fire it at something. So for his target, he fired his radiation gun at a very thin piece of gold foil. So I'm going to make mine yellow. Text box here, we're going to call that gold foil. So there's our gold foil. Why do you use gold foil? Well, it was the most bala thing ever. No, that wasn't the reason at all. Gold you can hammer very, very thin. And his hope was that you could hammer the gold foil thin enough that you'd only have one atom of thickness. And so what he did was he sat at the other side of this, and he used what we call a detector, a radiation detector. And drawing that is really complicated, so to show a detector, what we often use is an eyeball, because we say what you're doing is you're watching for something to happen, right? So he would sit over here and he would watch for the radiation to come through. But unfortunately, only about 90% of the radiation came through. Only 90%. Isn't that weird? So he said, well, maybe some of it's getting deflected a little bit. So maybe some of it's getting deflected, by a certain angle. So he moved his detector over a couple of angles. He tried a couple of different angles over here. And let me redraw the detector here. There's an eyeball. And he's looking over here, and what he sees is, he's missing 10%, but he only gets about 6 to 7%. Well, we'll put 7%. So, where's the rest of it? Where's the other 3%? So finally, he takes his detector and he places it behind the radiation gun. And what he sees is behind the radiation gun, he actually gets the other 3% or so. 2 to 3% depending on which experiment and what time he was running it. This was shocking to him. He never expected something as thin as 1 atom thick gold foil would be able to reflect. That is a reflection of radiation, and it came back towards the radiation gun. In fact, he was so shocked, he said, this is like firing a cannonball at a sheet of tissue paper, and having it bounce back. He wasn't the only one who was amazed by these results. Everybody in the scientific community was, but he gets credit for being the first one to observe it. He knew 2 things from this. All right, number 1, he knew that there must be a dense positive particle. And number 2, he knew that atoms must be mostly empty. That dense positive particle had to be at the very center of the atom, and all the rest of the atom had to be mostly empty space. It's kind of a neat discovery. Mostly neat because when you look at this model, you realize it's completely wrong. There's no way that positive particle, that positiveness is spread throughout the atom like that. So Rutherford decided to make his new drawing. What you must do is you have to draw you a nice circle here. Draw a circle. I'm going to draw this one in black. Right here, we're going to put at the very center of the atom a positively charged center. And that positively charged center is surrounded by the rest of the atom. He doesn't really know what the rest of the atom looks like. It takes us a little while to get a little more clarification on that. But he does know that there are electrons all around that. So we'll put some electrons around here. He doesn't know where they are. It's actually a few years after he does his work before we really start to discover where electrons are. But he does give that thing a name. He looks at that and he says, hey, it's in the center. Things at the center are called nuclear. So he calls this, oops, he doesn't call it nuclear, he calls it nucleus. The thing at the center is a nucleus. It's been a long day. It's almost over though. So the nucleus is right there. And then these things right here are the electrons. So what does he call this model? Well, he calls it the nuclear model. Some people call it the Rutherford model. Got a couple of different names there, but I like the nuclear model. Last but not least, we have Chadwick, who does an experiment I like to call beryllium bombardment. Okay? In the beryllium bombardment experiment, what he does is he's kind of borrowing a little bit from Rutherford here. Rutherford didn't mind because this is amazing work. What he does is he builds his own little gun, but instead of firing radiation, this gun fires, we'll make it red, this radiation fires beryllium. And I just now realized that this has the wrong word on it. This is not heavy water radiation at all. Let's change that. Let's mark through that right up there. Let's put another text box up here. This is beryllium bombardment. Beryllium bombardment. All right, so what does his gun do? Well, it obviously fires atoms of beryllium. Oops. Atoms of beryllium. So it fires atoms of beryllium out. And what he did, he tried a bunch of different things. And what he saw, one of the coolest ones they saw, was when you fire those atoms of beryllium at something like a block of boron, you get radiation out of that boron block coming out the other side. And that radiation is actually different from any of the radiation that had been dealt with before. It wasn't alpha, it wasn't beta, it wasn't gamma. It was literally called, somebody else had discovered this and they called it neutral. They called it neutral rays, is actually what they called it. And what Chadwick did was he took and he bombarded a bunch of different things and showed that you can get neutral rays from a lot of different kinds of atoms. And so it proved to him and to everybody else who read his work that there is a neutral particle inside the atom that has about the mass of a proton. Somebody else had already called it neutral rays, so he just said, hey, the particle of neutral rays is the neutron. And this is the discovery of the neutron. So Chadwick comes back into this model, and he basically says, you know what, this model is nearly exactly the same as my model. And so he, let's see if we can paste this in there. There we go. So he just says, hey, my model's about the same. The only difference here is in the center of the atom, instead of having just a plus, you also have a bunch of zeros. Right? There's a bunch of positively charged things and a bunch of things with no charge. And so he calls this the modern nuclear model. We call this too. Now, as it turns out, by the time Chadwick had done his work, we'd already done a bit to discover what happens to the electrons. But we'll worry about that next week. And there are the atomic models and the folks who discovered them, and then good, okay drawings. Maybe not the greatest drawings, but okay drawings about their experimentation.